Hi guys, welcome back to my YouTube channel. Today we are going to discuss about equivalence relation and partition. A relation on a set A is an equivalence relation if it is reflexive, symmetric, and transitive. We often use the type notation A, negation B to denote a relation. Also, when we specify just one set, such as A, B is a relation on set B. That means the domain and codomain are both set B or an equivalence relation due to transitivity and symmetry. All the elements needed to be a fixed element must be related to each other. Thus, if we know one element in a group, we efficiently know all its relatives. Define equivalence class. Let R be the equivalence relation on set A. For each A belongs to A, we donate the class of A defined as A is equal to X belongs to A and X relation to A. Define a relation. We are going to see some examples. Define a relation on Z by find the equivalence classes of the elements in the brackets is called the representative of equivalence class. An equivalence class can be represented by any element in that equivalence class. So, in example 6.3, 2, S2 is equal to S3 is equal to S1 is equal to set of S1, S2, S3. This equality of equivalence classes must be formalized in lemma 3.6.3.1. Notice an equivalence class is a set, so a collection of equivalence classes is a collection of sets. Take a closer look at example 6.3.1. All the integers having the same remainder when divided by 4 are related to each other. The equivalence classes are the same. It is clear that every integer belongs to exactly one of these four sets. Hence, z is equal to 0 union of 1 union of 2 union of 3. These four sets are pairwise disjoint. From this, we see that 0, 1, 2, 3 is a partition of z. Equivalence classes from partition. The overall idea in this section is that given an equivalence relation on set A, the collection of equivalence does not forms a partition of A. The converse is also true. A given partition of set A and relation is an equivalence mean. Theorem 6.3.4 as another illustration of theorem 6.3.3. Look at thus, S1, S0, S4, and S5 is a partition of set S. In order to prove 6.3.3, we will first prove two lemmas. If R is an equivalence relation of A, then A or B is implies A is equal to B. One may regard equivalence classes as objects with many aliases. Every element in an equivalence classes can serve as its representative. So we have to take extra care, but we deal with equivalence classes. Do not be fooled by the representatives and consider two apparently different equivalence classes to the distinct where it in reality they may be identical. We can easily show that is an equivalence relation. Each equivalence class consists of all the individuals with the same last name in the community. Hence, for the example, Jacob Smith, Liz Smith, and K.E. Smith all belong to the same equivalences classes. Any Smith can serve as its representative, and we can denote it as, for example, yours Smith. Hence, two positive real numbers are related if and only if there are having same decimal places. It is easy to verify that is an equivalence relation. Equivalence class X consists of all the positive and numbers having the same decimal parts as X has. Notice that R1 R plus minus U, which means the equivalence class where Z is equal to 0, 1 from the partition of R. Theorem 6.33 and 6.34 together are known as fundamental theorem of equivalence relation. If R is in the theorem 6.33, if R is an equivalence relation on any non-empty set, then the distinct set of equivalence class of R has a partition. The relation turns out to be an equivalence relation with each component forming an equivalence class. This equivalence relation is referred to as equivalence relation induced by P. I hope this video is helpful for you. Thank you.